In this video, we are going to learn a new way to represent complex numbers, a new form to write them in. This is called the polar form of a complex number. And for this, we need to remember what we learned last time about the complex plane. So this is a two-dimensional plane in which every complex number is represented by some point on the plane. We use these perpendicular axes, the real axis and the imaginary axis, to measure out the real and imaginary parts of a complex number as the horizontal and vertical coordinates of a point. So this point would represent the complex number x plus yi. Z is equal to x plus I y, and we could connect this point with the origin. This is something we've already done to get this vector representation of such a point. Here is where we realize, or we can notice, that there are not just the horizontal and vertical coordinates of that point which specify it, which can be used to locate it. So not just the real and imaginary parts of a complex number are the ones that can be used to specify it, but there are two other numbers, another pair of coordinates that can be used, and this pair consists of the distance of the point from the origin and the angle between the positive real axis and this vector pointing to z. Okay, so if we use these two quantities instead of x and y, we can just as well locate every point in the plane by saying how far we are going from the origin. That would give us an entire circle for possibilities, but then we would restrict this angle as well to tell in which direction we are walking that big of a distance. So this pair of coordinates is just as good for representing a complex number. Now we just have to find some formulas for r and phi in terms of the already given pair of coordinates x and y. Okay, for that, all we have to notice is that we have a right-angled triangle here, which can be used to express r and phi, well, x and y, using these two coordinates. Because if you remember your trigonometry, you would immediately write that if we want to express the cosine of phi, that would be, if we want to find the cosine of this angle, that would be the ratio of the length of the leg that is next to the angle. So that would be x divided by the length of the hypotenuse of this right triangle, which is equal to r. And similarly, we could find the sine of this angle by taking the length of the leg that is opposite that angle, that's y, and we would divide it by the length of the hypotenuse, that's again r. So in this way, if we take these two relations connecting x, y, and r and phi, we could multiply both of them by r to get x expressed as r times the cosine of phi, and y expressed as r times the sine of this angle phi. Okay, so at this point, let me just summarize quickly what we have done. We have introduced r as the distance from the origin to z. Now, we have a different name for this quantity. We also call it the modulus. Modulus of z. And we denote this modulus by the absolute value of z. So this is r. For the other coordinate phi, we can say that this is the angle between the positive real axis and the vector drawn to z from the origin. Okay, this quantity has also has another name. So this is the argument of z, and it's denoted by arg of z. So this is phi in this case. Okay, so now we have this terminology for these quantities, and we have seen how to express x and y using these coordinates. Now, if we go back to the traditional way of writing z, now we can just simply replace the real and imaginary parts x and y by these formulae, and what we get for z, instead of x plus yi, we get the following. Well, x is r times the cosine of phi, and y is r times the sine of phi. Let's just pull that r in front and write I times the sine of phi. This way we have expressed our complex number using this new pair of coordinates r and phi as r times the cosine of phi plus I times the sine of phi. This way of writing, expressing a complex number z is called the polar form of our number z. In contrast with that, we'll now can refer to this original way of writing a complex number as the algebraic form. Of z. Okay, so now we have two ways of writing, two forms to write our complex numbers in. Now I would like us to consider, well, look at the angle first, because there is some ambiguity about that. If we say that we want to measure this angle in radians, so instead of degrees we are using radians, pi radians is 180 degrees, then of course if we go around the origin multiple times we could arrive at the same point, so we should restrict the possible values of phi, and we will do that by saying that phi should be taking values between negative pi radians and pi radians, so between minus 180 degrees and plus 180 degrees. In that way we are making sure that phi is unique for each complex number. For each complex number we have a unique angle. Okay, and the only challenge is now to find formulas that are the inverse of these relations, basic meaning that we should express r using x and y and similarly express phi using x and y. Well, it's not too difficult for r to see that what we did before can be again used. It's a right triangle with hypotenuse of length r. So the Pythagorean theorem can be applied to find and express r, the modulus of our complex number, as the square root of the squared sum of the real and imaginary parts. Okay, so in that right triangle, these sides have length x and y, their squared sum under the square root should give us the length of the hypotenuse. So, and this is actually something we have seen in an earlier video. This squared sum appeared when we multiplied a complex number by its complex conjugate. So this is exactly what we get if we multiply z by its complex conjugate. We get x squared plus y squared. So we are taking square root to get r. Now what about the angle phi? We can use these relations to get to phi and express it in using x and y. All we have to do is divide the second relation by the first one. If we do that, what we'll get is y divided by x equals r times the sine of phi divided by r times the cosine of phi, which is, well, r cancels, and we are left with the tangent of phi, that is the sine of phi divided by the cosine of phi. So if we could invert this relation and obtain phi from this relation, then we would have a nice formula for the angle as well. Well, in order to do that, we have to apply the inverse function of the tangent function to this relation to find this angle. But you might have already noticed that this relation only makes sense if x is non-zero, because we don't want to divide by 0. So we have to take a few things into consideration, but we can, in short, say that phi is the arcus tangent, that is the inverse of the tangent function applied to y over x. So this is not always true. When x is 0, it's obviously it doesn't make sense. And even if x is not 0, so we get a number for this expression using, for example, our calculator, that number that our calculator would give us might not actually be the angle that we need between minus pi and pi. So we have to be careful, and that's why let me add the very important comment that not only this formula, but this formula together with considering the quadrants. And what I mean by that is we really have to be careful and look at the complex plane and see where our number, in which quadrant does our number sit. So let me give you two examples, two chances to test your understanding. So the first one, example, I want you to consider the number z equals minus 3 plus 3i, and I want you to find the modulus and the argument of this number, so the distance from the origin and the angle between the positive real axis and the vector drawn to this point. I want you to pause the video and input your answers below in the boxes. Okay, I hope you have paused the video and have found, using this formula for the length, the modulus of our complex number, with these numbers, that it is the square root of 18. So that's the length of z. And the argument of z, well, you could use this formula, but we also had to think about this number, negative 3 plus 3i. It sits somewhere along this line in the complex plane. Let's say that here is negative 3, here is plus 3, so this number would sit over there, and that angle between the positive real axis and z would be, so let me just write that this is negative 3 plus 3i, so that angle would be in radians 3 pi over 4, that is 135 degrees, 90 plus 45. Okay, for the second example, I want you to have a look at the number z equals minus I, and similarly to the previous one, give me the modulus and argument of this number. Pause the video and input your answers below. Okay, so I hope you have said that this number, negative I, has length or modulus that is minus 1. So this is basically pointing downwards 1 unit of distance from the origin. This is the number negative I, and it has the angle between the positive real axis and the vector drawn to it, that is minus 90 degrees, which is minus pi over 2. Okay, I hope you got it right, and I will see you in the next one.